5 years ago, the legendary physicist Stephen Hawking passed away, leaving a legacy of groundbreaking discoveries and also some theories as well. Most of these theories, however, were not finalized yet, so Hawking's death left scientists and enthusiasts fascinated by the world of science in jeopardy. Due to the fact that the English theoretical physicist and cosmologist was no longer alive, rumors started flying around about these theories. Well, it turned out to be that the late theoretical cosmologist's family had had enough with a series of rumors flying around about Hawking's theories, so they decided to confirm them. What theories did Hawking's family confirm, and what effect would it have on the world of science? Join us as we explore how Stephen Hawking died 5 years ago and now his family has confirmed the rumors. In his most significant contribution to science, Stephen Hawking proposed that black holes emit a type of radiation. According to him, this peculiar radiation would cause black holes to gradually ebb away before eventually disappearing in a massive explosion. Later on, this radiation came to be known as Hawking's radiation. This revolutionary idea introduced a conundrum of incompatibility at the intersection of general relativity and quantum physics, two of the most fundamental theories in the field. At the time, general relativity represented the closest thing we had to gravity at the cosmic scale. At the same time, quantum physics covered the most robust physics model governing the very smallest matter. And these two theories have been confirmed repeatedly since their distinct inceptions at the start of the 20th century, yet they remain frustratingly incompatible. The challenge arises from the absence of a theory of quantum gravity, which has led to a paradox known as the Hawking paradox. This paradox emerged when Hawking applied the principles of quantum physics to the edge of black holes in the mid-1970s, and physicists are still trying to solve this paradox. However, after 50 years of intensive research, physicists may have finally found a solution to the Hawking paradox, thanks to a recent review published in the journal Europhysics Letters, which sheds light on this cosmological puzzle. In this review, two researchers from the University of Sussex, Xavier Calmet and Stephen D.H., detailed the problem of the Hawking paradox and suggested potential solutions. So what exactly is the problem with Hawking radiation? Well, according to a 1974 letter by Stephen Hawking, quantum effects, which are not usually considered in the study of black holes, could significantly impact their mass throughout 10 raised to the power of 17, or 10 followed by 16 zeros. Now, black holes are formed when massive stars reach the end of their existence after exhausting their nuclear fusion fuel, leading to a collapse of their cores. With the fusion fuel gone, the outward pressure that supports a star against the inward force of its own gravity also disappears. This then results in a core collapse that, in turn, creates a point in which space-time is infinitely curved. To date, no physicist has been able to explain this central singularity. On the outer edge of this extreme curvature lies the event horizon of the black hole, or a point from which nothing can escape, not even light. And according to Calmet in Hawking's investigation of quantum effects, he realized that pairs of particles will be generated at random at the horizon of black holes. He said, looking at a specific pair of particles, he could show that one of the two, when produced at the event horizon, would fall into the black hole, never to be seen again. The other would escape and be, in principle, visible to an outside observer. This is the famous Hawking radiation. Now, when virtual particles emerge, they manifest with opposite charges to uphold the law of conservation of energy, which asserts that energy cannot be created or destroyed. And like a bank, the vacuum of space accommodates temporary deficits, yet this debt is promptly settled as the particles mutually annihilate. When a particle manages to escape Hawking radiation and evades annihilation, the remaining energy deficit must be compensated by the mass of the black hole. Consequently, the black hole experiences a gradual evaporation process as other particles come into existence, and more Hawking radiation is emitted, depleting its mass further. Calmet continued, Hawking radiation is thermal, and thermal radiation is pretty much featureless. This means that it cannot carry information about the object that emitted it. This would be a serious issue for black holes. He highlights that Hawking's calculations suggest that the information regarding the contents of a black hole would be lost during its evaporation. If this is true, it would pose a significant challenge for physics, since one of the fundamental principles of quantum mechanics, known as unitarity, implies that it's always possible to reverse the progression of events, akin to rewinding a movie. In other words, based on the radiation emitted by a black hole, quantum mechanics indicates that we should be able to reconstruct the entire history of the black hole, including its contents, explains Calme. If Hawking's proposition holds, we need to confront the notion that one of the well-established theories in physics is incorrect. We would either need to revise quantum mechanics or reconsider Einstein's theory of general relativity. Hawking's groundbreaking work demonstrated that black holes are not stable entities, but instead emit radiation and undergo decay. And remarkably, these insights extend beyond just black holes. When Hawking initially connected these pieces of information, his calculations revealed that black holes cannot remain stable with a constant mass. Instead, they emit radiation in all directions at a shallow temperature, known as blackbody radiation. This radiation moves away from the event horizon, and as natural radiation carries energy, the only credible source of this energy is the mass of the black hole itself. This phenomenon adheres to the well-known equation E equals mc squared, where the mass lost by the black hole must precisely balance the energy of the emitted radiation. And in an intriguing new research paper, physicists Michael Wondrak, Walter van Zuidelikom, and Heino Falke challenged the conventional notion that an event horizon is a prerequisite for the emergence of Hawking radiation. According to their alternative approach, this radiation arises solely from disparities in the quantum vacuum of space that depend on its curvature. Consequently, they propose that Hawking radiation should be emitted by all masses in the universe, including those without event horizons. This fascinating idea has been in development for quite some time. Let's delve into the reasons behind it. There is a common misconception regarding Hawking radiation's workings, popularized by Stephen Hawking himself in his widely acclaimed book, A Brief History of Time. Hawking described it as follows: "The universe is filled with pairs of particles and antiparticles that spontaneously appear and disappear due to quantum field theory and the Heisenberg uncertainty principle. In an uncurved space, these pairs always find each other and annihilate shortly after their creation. However, if an event horizon is present, one pair member can fall into it while the other escapes. This emits fundamental particles or antiparticles with positive mass energy outside the horizon. The paired member that falls into the event horizon is said to possess negative energy, which subtracts from the total mass of the black hole." While this depiction is convenient, even Hawking acknowledged that it must be flawed. In his 1974 paper, he even wrote, "It should be emphasized that these pictures of the mechanism responsible for the thermal emission and area decrease are heuristic only and should not be taken too literally." Indeed, in his 1988 book, which introduced this concept to the general public, Stephen Hawking does present this notion quite literally. However, it is important to understand that the portrayal cannot be taken literally because the particle-antiparticle pairs appearing and disappearing are not tangible particles. Physicists refer to as virtual particles. These particles serve as a computational tool to represent fluctuations in the underlying fields but do not possess the same characteristics as real particles. We cannot directly interact with or measure them in any way. Taking this depiction literally would lead to the mistaken belief that Hawking radiation consists of a mixture of particles and antiparticles. It primarily consists of highly low-energy photons arranged in a blackbody spectrum. Even the lightest known massive particles such as neutrinos and antineutrinos are far too heavy to be produced by accurate black holes in our universe. Instead, the actual explanation for Hawking radiation, while there are various valid approaches to calculating its effects, including those involving virtual particle-antiparticle pairs, lies in the disparity in the quantum vacuum between regions of space with different amounts of spatial curvature. This disparity in the fundamental properties of quantum fields in empty space leads to the generation of thermal blackbody radiation known as Hawking radiation. And within the workings of Hawking radiation, several intriguing points emerge that have been understood for many decades. First, Hawking radiation does not solely originate from the black hole's event horizon. One can calculate the energy density of Hawking radiation throughout space at any given moment, and by comparing this calculation to the expected energy density, an interesting disparity arises if the radiation were to originate solely at the event horizon and propagate outward. In reality, the majority of Hawking radiation generated near the event horizon stems from regions within approximately 10 to 20 Schwarzschild radii, the distance from the singularity to the event horizon of the event horizon itself, rather than originating precisely at the event horizon. Moreover, non-zero amounts of radiation are emitted throughout space, even at significant distances from the event horizon. While the event horizon may have a role to play in the generation of Hawking radiation, similar to how the presence of a cosmic horizon gives rise to Unruh radiation in our universe, relying solely on radiation originating from the event horizon fails to align with our theoretical calculations. Also, the amount of radiation emitted is more significant in regions of space with more pronounced curvature, indicating that lower-mass black holes emit more Hawking radiation and undergo faster decay than their higher-mass counterparts. This concept often perplexes individuals upon first encountering it. Surprisingly, the more massive a black hole is, the less severe the curvature of space becomes just outside its event horizon. The event horizon always serves as the boundary where the escape velocity of a particle is either lower or higher than the speed of light, defining the region outside or inside the event horizon respectively. Furthermore, the size of the event horizon is directly proportional to the mass of the black hole. However, the curvature of space near the event horizon of a smaller, low-mass black hole is significantly more pronounced than that near the event horizon of a larger, higher-mass black hole. Examining the properties of emitted Hawking radiation for black holes with different, realistic masses, we discover the following. The temperature of the radiation is inversely proportional to the mass. A 10-fold increase in mass results in a 1/10 decrease in temperature. The luminosity or radiated power of a black hole is inversely proportional to the square of its mass. A 10-fold increase in mass corresponds to a 100th decrease in luminosity. The evaporation time or duration it takes for a black hole to completely decay into Hawking radiation is directly proportional to the mass of the black hole cubed. A black hole that is 10 times more massive than another will persist for 1,000 times longer before complete evaporation occurs. At the same time, the degree of space-time curvature at a given distance from a mass is entirely independent of the mass's density or the presence of an event horizon. So let's delve into an intriguing scenario. Imagine for a moment that the Sun is instantaneously replaced by an object of identical mass. However, this object has different physical sizes. It can either have the same size as the Sun itself, radius of approximately 700,000 kilometers, a white dwarf, radius of around 7,000 kilometers, a neutron star, radius of about 11 kilometers, or a black hole, radius of approximately 3 kilometers. Now let's assume you are given the task of describing the curvature of space and how it differs between these 4 distinct examples. Surprisingly, the only discrepancies arise if you find yourself within the Sun's interior. Beyond a distance of 700,000 kilometers from the solar mass object, it becomes inconsequential whether it's a star, a white dwarf, a neutron star, a black hole, or any other object, regardless of the presence of an event horizon. The space-time curvature and properties remain unchanged. So combining these 3 points, a question arises. Does Hawking radiation exclusively occur around black holes, or does it manifest for all massive objects within space-time? While the event horizon plays a crucial role in Hawking's original derivation of the radiation that now bears his name, subsequent derivations in different dimensions have demonstrated that this radiation persists in curved space-time regardless of the presence or absence of an event horizon. And this is where the intriguing aspect of the new paper comes into play. The event horizon's sole function is to act as a boundary that distinguishes where radiation can be captured versus where it can escape from. The calculations are performed in a 4-dimensional space-time framework encompassing 3 spatial dimensions and 1 temporal dimension. These calculations share essential characteristics with other approaches that aim to determine the existence and properties of Hawking radiation. The boundary dictating what gets captured versus what escapes would still hold true for any other mass example we consider. In each case, the boundary for capturing or escaping radiation would differ. If we're examining a black hole, it would be the event horizon. In the case of a neutron star, it would be the surface of the neutron star. As for a white dwarf, it would be the outermost layer of the white dwarf. For a star, it would be the photosphere of the star. But regardless of the specific boundary, there would always be an escape fraction determined by the mass and radius of the object. The presence or absence of an event horizon does not hold any special significance in this context. We can draw a simple analogy between the approach Wondrak, van Zuidlekom, and Falke took in their paper and the Schwinger effect in electromagnetism. In 1951, physicist Julian Schwinger describes how matter could be generated from pure energy in the vacuum of space by creating a strong electric field. In the absence of an external field, quantum field fluctuations exist freely. However, when a powerful external field is applied, the vacuum of space becomes polarized, separating positive and negative charges. Under these conditions, virtual particles can become real, extracting energy from the underlying field to conserve energy. In the gravitational context, the analogy involves utilizing the curved space-time background as the equivalent of an electric field, replacing charged particles with an uncharged, massless scalar field. This field is a simplistic representation of the photons emitted through Hawking radiation. Instead of the Schwinger effect, the authors observe the production of new quanta in the curved space-time, with the production profile dependent on the distance from the event horizon. Importantly, nothing is inherently special about the event horizon. Production occurs at all distances sufficiently far from the object. Assuming the validity of the paper's analysis subject to independent confirmation, the main conclusion is the event horizon does not play a special role in producing radiation or other types of particles. In a more general sense, if we consider a quantum field theory involving creation and annihilation operators, subject to tidal or differential forces acting on the field fluctuations, this could comprise virtual particles and antiparticles if preferred. It then results in an additional separative effect compared to a uniform background of empty space. Afterwards, it logically follows that a fraction of the produced particles will escape in a manner dependent on the radius, regardless of the presence or absence of an event horizon. While this new research does not perfectly replicate all the known features of Hawking radiation, it presents a simplified model that substitutes for a realistic black hole. Nonetheless, the insights gained from this study and the underlying toy model have the potential to be highly significant for understanding the mechanisms and conditions that give rise to Hawking radiation. On the other hand, this work paves the way for constructing condensed matter analog systems where the effects of Hawking radiation could be quantified and observed. And a notable contribution of this paper is its correction of a widespread misconception regarding the generation of Hawking radiation at the event horizon. In reality, the event horizon acts as a cut-off point, preventing radiation generated inside it from escaping. Instead, there exists a specific radial production profile for this radiation. The peak amount of radiation is generated and escapes at approximately 125% of the event horizon's radius, and then the radiation gradually diminishes as the radius increases, asymptomatically approaching zero. However, a non-zero amount of radiation production can always be predicted. The specific consequences of Hawking radiation for objects that are not black holes are still a subject of ongoing research and investigation. While the energy source for Hawking radiation in black holes is the black hole's own mass, the implications for non-black hole objects are not yet fully understood. One possibility is that the emitted radiation could gradually deplete the self-gravitational energy of an object like a star or stellar remnant, leading to gravitational contraction. This contraction could have various outcomes, such as particle decay or phase transitions within the object. Another intriguing possibility is that Hawking radiation could have profound implications, suggesting that all matter could eventually collapse into a black hole under certain conditions and limits. This would mean that all objects, regardless of their initial composition, would eventually undergo gravitational collapse and subsequent decay through Hawking radiation. Is that really it? However, it is important to note that further research is needed to fully explore and understand the precise consequences of Hawking radiation for different types of massive objects and the implications for the ultimate fate of matter in the universe. These ideas remain speculative and can only be confirmed through further research. Nonetheless, this paper offers a remarkable approach, presenting a fresh perspective on a problem that's perplexed scientists for nearly half a century. It can potentially advance our understanding of the fundamental mysteries associated with black holes. While it is merely a suggestion at this stage, the possibility that all masses beyond just black holes could emit Hawking radiation is an intriguing implication worth contemplating. Now, the solution proposed to Hawking's paradox comes in the form of quantum hair, as revealed in two separate papers. In the first study, a team of researchers unveiled the complexity of black holes, indicating that their gravitational fields retain information about their formation. They demonstrate that the gravitational field of a black hole bears an imprint referred to as quantum hair, resulting from the collapse of matter into the black hole. Building upon this finding, the second paper, published in Physics Letters B, authored by Professor Xavier Calmet from the University of Sussex and Professor Stephen Hsu from Michigan State University, asserts that quantum hair resolves Hawking's black hole information paradox. This paradox arose from Hawking's proposition in 1976, suggesting that black holes obliterate information regarding their origins during the process of evaporation. This idea contradicts a fundamental principle of quantum mechanics, which states that any physical process can be reversed mathematically. Now, physicist John Archibald Wheeler coined the phrase "black holes have no hair" to describe the lack of observable features beyond the total mass, spin, and charge of black holes, as elucidated in the no-hair theorem. However, the revelation of quantum hair provides a mechanism for preserving information as black holes collapse, thereby resolving one of the most renowned conundrums in modern science. This discovery signifies a significant advancement in merging Einstein's theory of general relativity with quantum mechanics. Professor Calmet emphasizes that the resolution of this paradox does not necessitate a profound shift in physics, contrary to previous assumptions. The quantum hair phenomenon challenges the classical notion that black hole horizons are impenetrable barriers. Instead, in quantum theory, the state of matter collapsing into a black hole continues to influence the exterior while complying with experimental constraints. The identification of quantum hair sheds light on the intricate relationship between the interior and exterior of black holes, providing insights into the profound nature of these cosmic entities. It represents a remarkable step forward in our understanding of black holes and the reconciliation of quantum mechanics with general relativity. However, what do you think about these confirmed rumors? Do you think they have finalized Stephen Hawking's unfinished theories? Let us know in the comments section below.